Hi, welcome to section 1. This section corresponds to the week starting Monday, August the 31st. And so in this section, what we're going to cover is we're going to cover utility indifference curves and budget constraints. And so in a nutshell, what this material is going to be is going to be relevant concepts from intermediate micro, which you've hopefully seen, but we're just going to provide a little bit of review because it's going to be material that's going to be seen throughout the course. So let's jump right in. So in the first part of the class, what we're going to talk about is we're going to talk about why countries trade. And there's different possibilities for this. The first reason might be that they have different technologies. The second might be that they have different preferences. So different countries might like to consume different goods. So if one country likes apples and the other likes oranges, they might choose to trade with each other. Or different endowments. That is, different countries have certain resources, and these resources might vary across countries. And so we might think that countries are going to choose to trade based on the endowments of what they're given. So as I was saying, before we get into this sort of theories about why countries trade, first we want to review some intermediate micro knowledge. Oops. Okay. So first, let's go through utility. So we're going to define the term utility function, and a utility function is just going to represent preferences of a consumer. So it's going to take values from a consumption set X, where X could be, for instance, apples and oranges, just the set of apples and oranges, and then maps them to numbers on the real line, where numbers are going to tell us how much utility we get from the consumption of any given consumption zone. So we're going to denote a utility function with U, and we're going to find marginal utility as the change in total utility from change in consumption of a good by 1 unit of said good. Okay, so let's, that's the formal definition, but now let's talk a little bit more concretely about them. So in exercise 1, we're going to let our utility function, which is defined over the consumption set of apples and oranges, be equal to the number of apples raised to the 2/3 multiplied by the number of oranges raised to the 1/3. And exercise 1, part 1 asks us to derive the marginal utility of apples and the marginal utility of oranges. Or in essence, how much additional utility we gain by increasing apples by 1 and oranges by 1 at any point of how many given apples and oranges we already have. Okay. So the quickest way to do this is just to take the partial derivative of the utility function with respect to apples. Okay, and so by taking the partial derivative, what we're going to do is we're going to differentiate apples. And so what that's going to do is we're going to pull down the 2/3 on apples in front. And then we're going to subtract the exponent on apples by 1. So it'll be 2/3 minus 1. Or, in other words, it will be apples to the 1/3 times oranges to the 1/3. Of course, that simplifies. It'll just be equal to 2/3, and then the -1 means that we can just move apples to the denominator. And so in the denominator, it'll be apples raised to the 1/3, or oranges over apples all to the 1/3. And so that's our answer for the marginal utility of apples. You can see that the marginal utility of apples, the additional utility that consuming 1 additional apple gives us, is going to depend on the numbers of both oranges and apples we have. So let's compute the marginal utility of oranges, and on this time I'm going to go a little quicker. So we're just going to take the exponent on oranges, pull that down, so we get 1/3 oranges And then 1/3 minus 1 is negative 2/3 times apples raised to 2/3. So what does that equal? It's going to give us 1/3 apples over oranges. That's all going to be raised to 2/3. Okay, so that's how we compute the marginal utility of apples and oranges. So now let's go through and double check that that's right. So this is the solution here. And so that's what I wrote. Question part 2 asks whether or not the marginal utilities of apples and oranges are increasing as a function of apples and oranges respectively. Well, for the marginal utility of apples, we can note that apples is in the denominator of the marginal utility of apples. And so if we increase apples, that means that the marginal utility of apples is going to decrease. So the more apples we eat, the less we like every additional apple. Likewise, for oranges, the more that we eat of oranges or consume of oranges, the less that we care about an additional orange. And so that makes sense. If you have a lot of apples, generally the sort of the next apple won't be as enticing as the last one. Okay, and so the solution just says exactly what I said. Okay, so let's move on to exercise 2 and think about indifference curves. So an indifference curve we're going to define to be the locus of consumption points, which is going to give a given level of utility U. And so basically what we have is, just to make this concrete, if we have a utility function that is some function of both apples and oranges, then if we set our utility function equal to some number, say 10, or U bar is equal to 10, that's going to give us all the combinations of apples and oranges, which give us a utility of 10. In other words, it's going to be all the combinations of apples and oranges that leave us equally well off at a utility level of 10. And so that's one way you can think of it. So again, let's in exercise 2, let's use the same utility function, and we're going to draw the indifference curves for the combinations of apples and oranges such that utility equals 10, as well as 9 and 11, and we're going to use the following table. So this is just going to give us various combinations of apples and oranges such that our utilities are the given numbers that we have there. So let's plot this. You can see that at any given level of U, there's going to be a trade-off between apples and oranges. So, you know, if, for instance, we have a given number of apples and oranges, and if we weekly, so we either increase apples or we leave it the same, or increase oranges and we leave it the same, then we'll have more utility. In this utility function, more is always better. So as long as I increase one of apples or oranges and don't decrease the other one, then I'm always going to be weakly better off. And then notice that the indifference curves will never intersect for different levels of U. So it can't be that I can have the same combination of goods that gives me a utility of 9 and of 10. So every consumption bundle is going to give one unique utility value. Otherwise, we would be very confused as to what utility we would assign ourselves for any given consumption bundle. Okay, so we want all the xy points such that our utility function equals 10. So the way to do this is just to write, if we imagine oranges to be on the y-axis and apples to be on the x-axis, we want to write oranges as a function of apples. So we're just going to algebraically manipulate it such that oranges is a function of 10 to the third, or 10,000 divided by apples squared. And so we're going to plot this on the apples and oranges plane, such that any point on this curve is going to give us a utility of 10. And so doing so, you can plot it out yourself, but we've plugged in the numbers for you already. Looks roughly like this. So one value you can see that will give you a utility of 10 is if you just consume 10 oranges and 10 apples. And to see that, just recall that the utility function is equal to apples, I think it's to the 2/3, I want to say. Yeah. So apples to the 2/3. And then oranges to the 2/3. Or to the 1/3, excuse me. So then if I just plug in for 10 for apples and 10 for oranges, excuse me, that should be a 1, then those exponents combine and we're just left with 10. So indeed, that shows us that 10 apples and 10 oranges results in a utility of 10. And so the rest of the points you can just verify for yourself as giving the respective utility levels. Okay, so let's move on to the next point. So another definition that we have is the marginal rate of substitution. And it's the amount of oranges that one must give up to obtain another apple while maintaining total utility constant. And so, of course, you are going to want to think that this is going to depend on the relative utility gained or lost from the exchange of oranges for apples. And the marginal rate of substitution is just given by the slope of the tangent line to the indifference curve at any point. And so what's the slope of the tangent line? Well, in particular, that line right there is the tangent line to the indifference curve, to the utility function at point B. And so the marginal rate of substitution would just be given by the slope of that line in this example. Okay, so formally, what the marginal utility, the marginal rate of substitution is it's just the ratio of the marginal utilities gained from apples and then from oranges. And so the question 2 asks us to solve for the marginal rate of substitution in this example. And it's going to ask us why we say that the marginal utility is going to be diminishing. Well, to solve for the marginal rate of substitution, all we have to do is we have to go back to what the marginal utilities were. Okay, and then just recall that the MRS, or marginal rate of substitution, is mu apples over mu oranges. So what does that give us? So that gives us 2/3 over 1/3. The 3's cancel. And then that gives us oranges over apples raised to the 1/3. I'm going to flip this upside down because notice that this term is going to be in the denominator. So what I can just do is I can just write this in the numerator as oranges over apples raised to 2/3. And so what are we left with? We're left with 2 oranges over apples. So that should be our marginal rate of substitution. And let's get back to that slide. Okay, so as I showed, we get 2 oranges over apples. And why do we say that the marginal rate of substitution is diminishing? Well, we say that it's diminishing because as the consumption of apples increases, the amount of oranges that the consumer would give up to acquire an additional unit of apples decreases. And so this is going to make the indifference curve convex. So essentially, when you're consuming a lot of apples, you don't really value an apple as much as you value an orange. And so this is precisely what the marginal rate of substitution is saying. So the next question is, what prevents consumers from having more of both apples and oranges? As I said earlier, having weekly more oranges and apples makes the consumers always a weekly better off. So why wouldn't they just have always more? Well, the answer is simple. It's just that they have a limited income, and so they eventually have to make a trade-off between purchase of apples and oranges in order to not exceed their budget. And so in part 3, we're going to write down the budget constraint and solve for it as a function of apples. And so what is going to be the slope of the budget constraint? Well, the solution is going to be that the consumer wants to maximize their utility, but they're going to be constrained by their budget constraint. So their total income cannot exceed their expenditures on apples. So the expenditures on apples, or the amount they spend on apples, is just going to be given by the amount of apples they consume. So this is just the number of apples purchased. And then just times whatever the prevailing market price is. So this is just the price of apples, or P of apples, as we'll frequently write. Okay. And then likewise, they can also spend their income on oranges, and so this is going to be the expenditure spent on oranges. Okay. So suppose that we want to write oranges on the y-axis, and then do everything in terms of the prices of apples and oranges, and then of the number of apples consumed. So what we'll do is, suppose we have I is equal to P apple times apples plus P oranges times oranges. Well, then if we subtract P apples times apples from both sides, that'll give us this expression, P orange times oranges. And then all we have to do to get the expression shown above is we just divide on both sides by P oranges. Those cancel. Here we get P apples over P oranges, and here we get income over P oranges. Okay, so in total, the expression is just oranges equals total income over P oranges minus P apples over P oranges. So essentially, if recall that we said that apples was the x-axis and oranges were the y-axis. So then in orange, in sort of apple-orange land, we have that the slope of this curve is going to be P apples over P oranges with a negative slope. So that's going to be the slope of the budget constraint. In essence, it's just showing what the trade-off is between apples and oranges monetarily. So suppose you're told that the consumer has $60 of income, the price of apples is 4, and the price of oranges is 2. So what we want to do here is we want to just write down the consumer's budget constraint. So the budget constraint, it's just going to be plugging in for the prices that we had before. And so the budget constraint here, 60 is now our income, so 60 must be equal to the price of apples times the amount of apples we buy, times 2, which is the price of oranges, times the amount of oranges we buy. Okay, so what we're going to do in part 5 and part 6 is we're going to draw the consumer's budget constraint. And in part 6, we're going to talk about at which point the consumer's utility is maximized given their budget constraint. And we're going to mark the optimal consumption level. So we've already drawn the budget constraint. Note that if the budget constraint is 60 times 4 apples plus 2 oranges, then what gives us an income of 60? Well, if we spend it all on apples, then 60 times 15 apples will give us the total amount of apples that we can buy. Or we could spend it all on oranges, then the price of oranges is 2, so we could spend up to 30 oranges. And so this is the total amount of oranges we can consume, and this is the total amount of apples we can consume. And recall that I said that the slope, so the slope here is given by P apples over P oranges. And so the price of apples is 4, the price of oranges is 2, so the slope here is -2. At which point is the consumer's income maximized? Well, they could consume at point D or C, but notice that that gives them a lower income, and so a lower utility value, and so instead they'd rather consume at point B, which gives them a utility of 10. And so they'd rather consume exactly at where the budget constraint is just tangent or just kissing their utility curve, and so that is point B. And so this is saying what I just said. Point A is unobtainable given the budget constraint. Points C and D are obtainable, but they give the consumer a lower value of utility. So the optimal point is going to be B, where the indifference curve is tangent to our budget constraint. So in the previous steps, we found the optimal utility maximizing bundle is going to occur at the point where the slope of the budget constraint is equal to the slope of the tangent line to the indifference curve. So algebraically, what we're going to express this as is that the slope of the indifference curve at a given point has to be equal to the slope of the budget constraint, or that the marginal utility of apples over the marginal utility of oranges has to be equal to the ratio of the prices of apples and oranges. So rewriting this, what we have is if we simply divide here by apples by P apples, so if we divide P apples on both sides, and we cross multiply, so we multiply by MU oranges, these cancel, and so what we get, so we got the expression below, where the marginal utility of apples over the price of apples has to be equal to the marginal utility of oranges over P oranges. And this makes sense. So the reason that this makes sense is that consider that each of these terms is essentially saying how much marginal utility you're going to get per every dollar. And so, for instance, suppose that instead of being equal, the marginal utility of oranges per dollar spent on oranges was higher. Then our consumer, they'd want to give up some apples and instead consume more oranges because they know for each orange consumed, they are going to get more utility per orange. Likewise, if instead we had that the marginal utility of apples was per dollar spent on apples was higher, then our consumer would give up some oranges because they'd know that for each apple consumed, they'd gain more utility. And so in equilibrium, what we'd expect is that consumers are balancing apples and oranges such that they're getting the same amount of marginal utility per dollar. And so this is the way that I most intuitively think of this rule. Likewise, you can think of this in terms of different ways. So the other intuition is that P apples over P oranges is the market price of apples in terms of oranges, and the MRS is the price of apples in terms of orange valued by the consumer. And so what this is saying is that the amount of apples, if the MRS is telling us the amount of oranges that we're willing to give up to gain one apple, and the price is how many oranges, if we don't buy, we could buy an apple instead, and we'd want to equate those two. And so likewise, we can go back through this logic and we can say that if the trade-off is such that the ratio of apples to oranges is higher than the marginal rate of substitution, then apples are going to be relatively expensive and they should consume less apples and more oranges. If the price of apples, the relative price of apples is lower than the marginal rate of substitution, then apples are going to be relatively cheap and they can consume more apples. Thus, we're going to get that the relative price of apples should be the same as the marginal utility of apples in terms of oranges. And that's going to be our utility maximizing law. So in part 8, what we're going to do is we're going to solve for the utility maximizing bundle again using this algebraic approach. Okay, and so how are we going to do this? Well, we're going to use this rule and MRS is 2 oranges over apples. And then that has to be equal to the price of apples over the price of oranges. And so what is that going to give us? Well, recall that the price of apples is equal to 4 and the price of oranges is equal to 2. So this is 2. And then what we're going to do is then what we'll have is if we divide on both sides by 2, then we'll get that oranges over apples is equal to 1, or implying that we should consume oranges equal to apples. Okay, this doesn't tell us how many apples and oranges we need to consume, just that we need to consume them in equal proportions. So to do this, what we're going to do is we're going to go back to our budget constraint. And recall that our income was 60, price of apples was 4 times the number of apples, and the price of oranges was 2 times the number of oranges. So then what we can do is we know that apples is equal to oranges. So if I take this formula here, just bring it down here, then I know that 60 is going to be equal to 4 apples plus 2. And now here I'm going to plug in for oranges with apples. So I got 2 apples. What does that give me? That gives me 6 apples. So if I divide on both sides by 6, then I get that I need to consume 10 apples. And likewise, we know that oranges is equal to apples. So the optimal consumption bundle is such that oranges and apples are equal to 10. Okay, and so the slides are just showing the exact same thing.